Good morning, everyone, and let me welcome you on our second English engineer workshop in Servo Drives. So I'm Adrian Buryło, product leader in Servo and Motion Group. Together with me, Błażej Siudaj, product manager of the same product group.
Good morning.
And today we will speak a little about the predictive maintenance in servo drives. But before we'll go to the main topic, let me say some organization things about what will be present and what will be done in this, let's say, click meeting. Because maybe not everyone is accustomed with click meeting platform. So firstly, about the questions. If you will have any question about the topics that we will show, then just write it down on chat. But to write it down on chat in this Q&A section, and later we'll just answer this question on the end of whole, let's say, webinar. Yes, so approximately after 1 hour, because this webinar will be, let's say, divided in two sections. The first one in which me and Błażej will present, and the second one in which our technical leader in servo drives, Adam Syrek, will present. He's already, let's say, warming servo drives in testing area, and he will show more real application of this predictive maintenance function in servo drives. Secondly, on the top, you can see this green button on blue background. This you can click it and register for some kind of, let's say, consultation with us if you will be interested in this predictive maintenance function in drives that will show. You can always in any time on the presentation just click it and register. It is for free. We will then contact you later in the time that you will be available and talk about how predictive maintenance function can help you in your factory. So I think that's all from these organizational questions. So we'll go to the presentation. Once more question: do you hear us? And do you see us?
Please write on chat.
Yes, please write on chat. You can also write anything you want on chat, not only the questions. So if you can hear us, can see us, and can see the presentation.
Thank you for
Good.
feedback.
Good, thank you. Okay. So Błażej, what is like with this predictive maintenance?
Slow. Because before we get to that, let's first have a look at the evolution of the approach to maintenance. Starting from the very beginning, we first had what we can call a reactive approach. In other words, when a machine doesn't work, we know it has broken down. It's easy to guess that this generates a lot of problems. And the breakdown is usually surprising, which overall results in us losing money because we are not producing. And here we either have to have a large warehouse with all the replacement parts, or we end up with longer delivery times and waiting for replacement to be delivered, which is in recent years, especially in delivery crisis, supply problems could quite effectively block our production.
Okay, so when we are talking about the reactive maintenance, I have one example as old car, for example. Let's imagine we have a Mercedes W123. Yes, so quite an old car for me, exactly. So in this Mercedes, there were no sensor, etc. Yes, no additional functionality. So when something broke down, we just found out about it while driving. Yes.
Yes. And in industry, such an example could be, for example, broken mechanical parts. We know that something has broken when the mechanical part, when the machine is not working. The second level of development is a preventive approach to replacing critical machine components. In other words, we have a line or machine shut down once in a while and replace anything that might break down. There are examples of such machines or production lines.
Okay, so this, for example, makes me think of an airplane, yes, where for our safety, of course, we have a small inspection of the plane before every takeoff and periodic major inspection every so often.
Yes, exactly. It's a good example. But this is an extreme example, although we know of such cases in industry too. On the other hand, for economic reasons, wore-out components are replaced more often, and those that are still reasonably good are left for the next maintenance stop. Such an example of general maintenance shutdown can be described as a holiday shutdown in manufacturing companies, where operators are on holidays and maintenance services preventively inspect and replace necessary components.
Okay, these are very nice examples, but in the end, what about these drives?
Okay, reactive approach doesn't interest us, and we had preventive maintenance implemented in drives already a long time ago. In J3, we already had information on the number of times the drive was switched on and the number of operating hours completed, for from which and from which an approximation of the potential further service life of the drives is created. These values refer to the most wearing part, which is the smoothing capacitor.
Okay, but J3, these drives were released almost like 20 years ago?
Yes, that's right. An idea of preventive approach is nothing new.
Okay, then what about this more new function, let's say, functionality prediction, yes?
Yes. So finally, we have now reached the pinnacle of the evolution of the approach to maintenance. It is linked above all to this whole idea of Industry 4.0 or IoT, which means that machines are becoming more and more sensorized and we know more about what is going on inside them. Moreover, it is not always the typical parameters that we might want to measure at first glance that are being measured.
And what do you mean by this?
The point is that in many cases, we can use additional physical phenomena to find out indirectly about the state of individual components. For example, analysis of vibration or even oscillation in relation to bearing wear, analyzing of current characteristics in a motor in relation to changes in, for example, friction or movement resistance, or another example, for example, increasing the component temperature means increasing, for example, resistance to motion.
Mm-hmm. So now we can replace worn out components before the end of their life without the risk of unscheduled downtime and at the same time save on cost as well as taking care of the environment and reducing the carbon footprint, which is, let's say, a trend, a very popular trend right now. So for me, in theory, it seems super cool, let's say, yes. But when I think about it, I see that we'll need hundreds of sensors, and we'll be processing huge amounts of data. And I see that here is emerging very massive projects. It will include analysis of needs and planning, system and vendor selection, of course, yeah, of course, yes, then hardware installation, the configuration of this hardware, and finally software implementation. But this is not the over because there are tests, optimization, yes, and finally deployment at scale, and then monitoring, yes. So there are a lot of stages to do. Uh, and unfortunately, this is not always the best solution because this kind of applications are expensive to implement, require specified stuff to make a code, and writing this code takes huge amount of time due to data analysis, which needs to be done beforehand, yes, and it needs to be customized for every application. And the worst part probably is fact that even after all that job, which can take several months to complete, as you can imagine. The prediction accuracy can be very low, like 50%, and even in fact 70, 80% accuracy is a very good result. So shortly, I would say implementation has a high level of risk.
Yes, and in summary, we have two types of applications. Those in which it is possible and worthwhile to take an interest, and second, and those where implementation will be difficult and not justified economically or for other reasons. I would like to ask you, Adrian, what the market thinks about this. What is the trend or interest in this subject?
Of course, I can discuss this. Look, for example, at the IoT analytics reports regarding the predictive diagnostic market. And already a year ago, the global market was valued at $5.5 billion. Yes, so huge amount. Of course, this result is scored by a very large companies with several hundred thousand employees. So companies that can afford to take a lot of investment risk, the risk that I told you before. But the upward trend is undeniable. And based on even a less complex indicator, so the number of queries on Google, it can be seen that the number of queries of keywords for predictive maintenance exceed the number of queries for condition-based diagnostic, as you can see on this trend around, I don't know, 2018 year. Yes. So in short, this trend is not just visible. It enters through the window of your home and sits comfortably on the seat saying, are you ready? Well, but one time we say expensive and only for big companies. The next time it's best to invest now because the race will start without you. So decide, Mitsubishi. Yes. Fortunately, the report points to one more thing, because one of the three dominant trends regarding the predictive maintenance is the interest in complete solution, offering pre-trained models. And thanks to the fact that these solutions are tailored to specific devices by manufacturers, the accuracy of prediction is high, and implementation itself is much, much easier, requiring no expert stuff.
So, MySart? And MySart is the work of Mitsubishi Electric, otherwise it is our own technology. And based on deep learning and data analysis, accelerated learning, process knowledge, and heuristics, which we can use for various interesting purposes, which ones? Here are some examples. First one, I would like to show you quite interesting example, a solution to detect the use of violence through advanced analysis of posture data. The data is extracted from the monitoring. Effectiveness around 90%.
Okay, and something more closer to us.
Okay, other example implemented in cars, analysis of the driver conditions while driving and detection of life-threatening situations, for example, like falling asleep or others.
Okay, sorry, Boże. These are very nice examples, but I would like, and our viewers probably also, something more from industry.
Okay, so one example could be Melfa Smart Plus card, which can install in our robots from Melfa series. Among other things, it allows us to use the predictive maintenance function in the robots. We are already close to our servo drives because there are servos inside of the robot. However, in the case of robots, where we have known kinematics that have been tested and thoroughly optimized, it's easier for us to implement predictive maintenance. Knowledge of the kinematics, internal motion resistances, and loads, in result, gives us very high reliability and accurate prediction of the system. Our experience showed that this works well, and it's confirmed by increasing popularity of this solution. Also, it's important that we can add such card to the robot at any time and start working with predictive maintenance even in already existing application with Melfa series robot. However, in case of the servo kit itself, which is not equipped with ready-made and well-known mechanics, the situation is not so easy, And here we come to the core of today's topic.
Yes, because this is ultimately a webinar dedicated to servo drives.
Yes. So, Adrian, which features of the servo drive allows us uh, to be used in predictive diagnosis?
So generally, Mitsubishi, we believe that a servo is a sensor, not only the encoder, of course, because this means that a servo can act as advanced sensor in the application from which a lot of useful data can be extracted. But for this to be possible, the servo must meet certain parameters. So, for example, high speed frequency response and very big encoder resolution, yes, because it allows very accurate data about the current, speed, and position characteristic to be collected, which, let's say, translates into effective auto-tuning algorithm, and this allows static and dynamic motion resistances to be estimated by the drive. In J4, so the previous series, we already had some function which allowed us to collect data about the movement resistance and so on, but not as developed. And let's go back to the present right now, yes, because J5, the newest series, uh, in this series we have Maysart. That is to say, as standard, without additional fees or licenses, the servo amplifiers are equipped with algorithms that can be used for prediction. And what these algorithms allow us to do? So firstly, to estimate the dynamic parameters of resistance to motion.
That is, we can check wear and tear of the spindle or in-end bearing linear bearings, as the parameter will increase with the wearing of the mechanics or even a lubricant. What is more, we will be able to see if someone has carried out maintenance, and we will also be able to check remotely throughout communication with the drive the change in value of this parameter.
Yes, and secondly, to estimate the static resistance to motion of the drive.
That is, this can be used for check for changes in belt tension. In other words, belt stretching over time or slackling can be detected.
And thirdly, to check backlash value in the mechanical transmission or in rack.
Yes, but it depends on the precision. In low precision gears and rack with large wheel diameters, it will work. How about showing how it works in animation?
Of course, I can do that. So this is the animation about the machine diagnosis function, and we'll see some examples of the usage of each of these three functions that we mentioned. So firstly, we go with the ball screw, of course. And here, let's see, we have the typical manipulator. This work in some electronics. What happened? So firstly, our function that later Adam will show us, they are collecting the data and monitoring by 90 hours how the machine is responding. With this data, they will set the ranges where, let's say, we have the ranges of normal work. And after a few months, few years maybe, when this range will be exceed, we'll have the alarm on the servo drive. Uh, of course, this alarm will not, let's say, stop the normal work of the servo drives, but it will be just the information that we can, for example, send via the network, via CC-Link ITSN or via the Ethercat to SCADA system, to HMI panels, and the operators can see the alarm in the history, yes, and then replace the parts or just do the maintenance on of these parts and do the downtime. Then there is the belt. Very similar situation here. We are checking just different things, different parameters. Also 90 hours of learning after that in normal work, because learning is also in normal work. Yes, so normally we have the machine, we have built machine, it is working, then in 90 hours it is learning the ranges, and automatically after setting the ranges it will check, yes, and after some time also it will give the information that there is some problem. Yes, for example, here with the tension of with the belt, and the operator have to remember that, okay, so we are checking the alarms, we have the alarm and we'll have to do something about the maintenance of the belt. Yes, so for example, tension it more. And now the backlash function. So this function is working differently because it is not working like in normal work of the machine, because it needs the machine needs to be stopped. It is working in the service mode. Yes. So for example, on the start of the machine, on the first start of the machine, we are checking the backlash of the gears of the rack. After that, after some time, for example, after a month, when the machine is not working, we are just starting the machine for the, let's say, a new week. Then we can always check via our software what is the backlash. Yes, and then after some time also check. And when this backlash will be too much, yes, it will be too big, then we'll think, okay, so we will have to do the maintenance on this mechanical part and check what it is about. For example, replace it later.
Yes. So let's see how it works, how it looks like in reality. Adam, can you hear us?
Okay, so we are waiting for our technical leader. Once again, we want to remind you that on the top you have this, let's say, blue bar with a green button, and you can register for the consultation with us, in which we can show you the implementation, maybe not the implementation, but we'll check with you if this machine diagnosis function that we were talking about is right for you, or if it fits for you. Okay, now voice to the Adam, and we are turning off for now.
Hello. I will talk about machine diagnosis function a little bit more deeply from the technical point of view. And first of all, I will explain how the basic machine diagnosis function works, and then I will demonstrate it on our set, how we can use it, or what kind of data we can get from the machine diagnosis function. So let's start from some more technical introduction. So we have few functions related to machine diagnosis function that Adrian and Błażej show on the animation. But let's see, I will go a little bit more deeper with it. So first, two mechanical systems that we can diagnose is a ball screw and its linear guide. So for this function, we can use mostly two things. Once we can estimate the friction, and then based on this friction, we can judge some levels on the friction that is proper for the machine or it's not proper for the machine. And that's the role of the amplifier, to find out this value, this border, when we can say that something wrong is happening with our machine. And the similar thing with vibration. So we can monitor the vibration, we can check the level of the vibration on the machine, but also amplifier can judge if this vibration is on the normal level, that is normal for this machine, for this mechanical system, or something wrong happened and this vibration level is increasing. The next mechanical system that we can somehow diagnose is the belt. So we can measure or we can judge if the tension of the belt is the proper or it's not proper. And generally, this mechanism based on the static friction of the axis. And the last mechanical system that we can somehow diagnose in our servo amplifiers, using our servo amplifiers, is a gear. And here we can measure the backlash on the gear, and we can judge if this backlash is on the proper level or it is too high. So let's review all of these functionalities. And first of the functionality that I will describe is a little bit other functionality, not mentioned on the previous slide. It is total travel distance failure prediction. So it's not the predictive maintenance, it's more not predictive, but preventive maintenance, because here we measure the distance that that the axis traveled, and based on this distance, we can make some maintenance or something like that. If we have some mechanical system like the bore screw, like the linear guides based on the belt, in the detailed manual, we can find out that after some number of hours, that should be the maintenance, but also after some travel distance of this mechanical system, we should make some inspection, some lubrication, and so on. So using this function, once we can measure the distance that was made by the axis on the amplifier, but we also somehow use this function, or amplifier use this functionality also in the other functionalities that I will describe later on. So here, basically, we input to the servo amplifier some kind of the limit, and if the limit is exceeded by the real axis, the warning on the amplifier occurs, on the axis occurs, and we know that we should make some inspection of this axis. So the next thing is the vibration. So I think it's one of the most important thing, one of the most significant thing that indicates that something wrong can happen with the axis if the vibration occurs on the axis. So if we have the ball screw and we have some backlashes on the linear guides, if something is not correctly fixed on the axis, this vibration can occur, and it has bad impact generally on the functionality of the machine, and it can additionally make the problems with this axis, and it may cause the faster usage of this axis. So general amplifier allows us to measure the vibration level. It is the vibration of the torque, because it's mostly showing us what happens on the axis. So if there are some vibration, or if there are no, so most significantly we will see it on the torque. And here we can measure the level of the vibration, and it is in the percentage of the nominal motor torque. So it's the value that we are measuring, because we have different motors and different values of the torque. So we generally, if we talk about the torque in our systems, in our amplifiers, we talk about the percentage of the nominal motor torque. And also we can get the information about the frequency of this vibration, if this vibration has some, say, meaningful frequency. And we can measure, or amplifier measure these values also for the stopped machine, for the stop axis. So we can see if something happens when the axis is stopped and when the axis is rotating. So in those both states, we can measure the level of the vibration, and we can measure the frequency of the vibrations. And what is, I think, most important here, amplifier during the time can estimate what is the can measure this vibration and can estimate what is the proper level of the vibration for this axis. And if something happens in the time that this vibration level goes up, increases above some level, it will cause an error, or it will cause a warning, not error, because it will not stop the application. It will just gives us the information that the vibration level of this axis is too high. So we can go to this axis and we can check what happens, if it is really normal, or we should do something to correct operation of this axis to avoid some stop of the to avoid the stop of this axis in the future. So that was the vibration. The second thing And also very important in the machine diagnosis functionalities in the amplifier is the friction. So generally, amplifier can estimate the friction on the axis, and it can estimate dynamic friction and also static friction in both directions, in forward direction and in reverse direction. And once again, it is related to this friction is not, let's say, exactly the friction that we know from the lessons of physics. It is mostly related to the torque of the motor. So how much torque motors needs to overcome this kind of the friction. And in case of the dynamic friction, is exactly the torque that is needed to overcome the friction at the rated speed of the motor. So it will be once again in the percentage of the nominal motor torque. And the static friction is some kind of the friction that is necessary, let's say, to start or to make the axis moving. So it's not maybe exactly the static friction, once again, that we know from the physics, but it has some relation to the operation of the axis that we can use in other functions later on. And to estimate this friction, because this function generally works in almost all amplifiers, the same as the vibration estimation. So if you have Mitsubishi amplifier starting from MRJ4 series, MRJ4, B, A, GF, MRJ5, the vibration estimation and also friction estimation works always. Yeah? So it is default functionality of our amplifier. And in case of the vibration estimation, without any condition, it works, and we can read the values of the vibration. But in case of the friction estimation, there are some conditions how it should work to properly estimate this friction. And once it needs some time, and it needs to work in some levels of the speed of the motor. So we have to set parameter PF31 that divides our movement to two ranges, the high speed movement and low speed movement. So in all of these ranges, the amplifier should work at least 150 seconds to properly estimate the friction, the static friction and dynamic friction on both directions. So in both directions, at least this 150 second amplifier should work. So generally, to estimate all these parameters, we need few minutes, or amplifiers needs few minutes to judge what is the level of the friction in both directions. And once again, like it was in the vibration, here we have the same in case of the friction. So if the amplifier is working for the longer time, it can check and it can estimate what is the proper level or expected level of the friction on this axis. And if this friction goes up or below this estimated threshold, or amplifier gives us the information that something may be wrong with this axis. And based on that, we can once again make some inspection, check the axis to prevent the breakdown of the axis. Yeah, and those levels are calculated automatically after some time. And this time generally is at least 90 hours of operation, and at least once it should operate for the 3 hours or longer without the stopping or without turning off the machine, because it also takes into consideration, takes into the parameters the impact of the temperature of the axis to estimation of the torque and so on. And so quite a lot of factors is collected together to estimate, to find out these proper levels. And as I said, it can be made automatically by the amplifier, but we can also set these levels by ourselves. So if we know what we should expect, or we see the levels of the friction that are estimated, we can say that we don't want to have more than something, and we can set those levels by ourselves, or if we have, or if somebody is the machine builder that it builds the same machines few times, so it can, let's say, estimate the friction level, or it can let the amplifier to estimate the friction level on one machine and then copy these parameters to the other machines, and in this way checks if the mechanical part of this machine is correct or not. Because if after assembly the levels of the friction are are out of the ranges, it means that something is wrong on the mechanical part of the machine. And so if we talk about these levels for the friction, but also for the vibration, we can set those levels by ourselves, or we can let amplifiers to estimate these levels by the amplifier. And here, in case of the friction failure prediction function, we base mostly on the dynamic friction. So it's the value that is, let's say, taken into the consideration, and it is useful mostly for ball screws and for linear guides. Because if something wrong happens, in most cases, this parameter changes. So it can go down if there are bigger backlashes and the friction goes down, but it means that the precision of the application may be worse, or it can go up. The friction can go up if there is some problem with greasing or something like that. And we can also estimate the static friction. And the static friction is useful for judging the belt tension. So it's the next topic that I would like to talk about. So if we talk about the belt tension, we talk about the static friction, because there is some correlation between the static friction that is estimated by the amplifier and the tension on the belt. So if the tension is higher, the friction is also higher. And based on this mechanism, we can judge if the tension of the belt is correct or it is reduced. And we can use this functionality in two ways. One is a little bit more simple, and second is it's a little bit maybe more complicated, or it needs some more parameters setting. So in the first case, static friction failure prediction function, so we do the same as with the vibration and with dynamic friction. So generally we let the amplifier to set some limits. So we start the amplifier, let them estimate the static friction, let them calculate the levels, the threshold, and we are checking if there is warning or not. So almost nothing we need to do in this case. But the second option is a function that is called belt tension deterioration prediction function. And in this functionality, using 4 parameters, we can set up the relationship between the static friction and belt tension. And after that, the amplifier estimates the tension of the belt, and we can set some value, the limit value of the tension in the parameters. So in this case, we need to set these values. We need to find it out in some documentation of the linear system and set those parameters by ourselves. But we have the, let's say, more accurate data in this case. So using those two functionalities, we can judge, we can diagnose the belt condition in our application. And the last mechanical system is the gear, and here we can measure the backlash on the gear. So in case of this application, we have to, or amplifier executes some predefined movement. So in case of all previous functionalities that I was talking about, it happens somewhere during the normal operation of the amplifier. So during normal operation of the amplifier, it measures the friction, vibration, estimates the proper levels, and we don't need to stop the machine, we don't need to execute something extra. But in case of the backlash estimation, we have to start some procedure from HMI or from the MR configurator. And in this procedure, the amplifier is moving forward, reverse, to reduce the backlash in one direction, and then starting in opposite direction, it can judge what is the level of the backlash. So after that, we have the result in the degrees of the axis that we are using. And additionally, in the parameters, we can set the level of this of the backlash that is allowed for this gear, and if the measured backlash is greater than this limit value, it will also show us a warning that the backlash is too high. So it's just simple, let's say, comparison, but we have this information in the parameters. So during the procedure of checking the gear, we don't need to have this data with us all the time, because we have it in the amplifier, and we have the simple information if it is correct or if it's not correct. And if we have all this data in the amplifier, like friction, like the levels of the friction, information if it's correct or it's not correct, we would like to use it also somehow to make some reports, to send it to some higher level of the information system in our factory. So we can use the dedicated function blocks. For example, there is a lot of possibilities how to get this data. We can use HMI. We have dedicated screens that I will show how does it look like. Or we can use just the dedicated function blocks to read the objects from the amplifiers, because in the amplifiers we have all this data related to machine diagnosis function in the specific objects that we can just read to the PLC and use it somehow in our system. And also sometimes we can use this data like the estimated friction, estimated vibration, to log it in our systems and to measure the trends on our side. So we can use the amplifier and the intelligence in the amplifier to let them judge the level of the vibration, for example, or level of the friction. But we can also log this data in our system, see how the trends are looking like, and if something is happening, or if the level of the vibration friction is all the time the same. That means that the mechanical part should be proper. So that's all regarding the presentation part. And now I will try to, let's say, show you a few functions on our demo set, but I need to switch the view to other camera. Okay, and now you should see our demo sets, few axes that I will use to demonstrate the machine diagnosis function. So let's start from the, let's say, beginning. So the most easy function, I think, is this total travel distance function. So if we have the axis and we start the axis, we can see that the level or the movement distance is changing. And if this movement amount exceeds the level, it will cause a warning on the axis and most, as I see on the axis number 2, no. Because here we have the read value. Let me start this axis. Axis number 2. Almost good. Okay, axis number 2 has some vibration, that's why I stopped it. And so axis number 2 is moving. It's this wheel that you can see here. And if I, let's say, refresh the data, because in MR configurator we have to refresh this data all the time. So here we can see that we have 350 almost revolutions, and it measures the revolutions of the amplifier. So if it reaches or it exceeds the limit that is set here in the parameters, it will cause a warning that the number of revolutions of the travel of this axis is higher than it was assumed. So very basic functionality in case of the machine diagnosis function. The second functionality is the vibration estimation of the axis. So also for the second axis, we can see that we have some vibration, and I hear that there are some vibration. And also during the stop and during the rotation, we see maybe not such a big, but there is some level of the vibration, and it exceeds the limit. So it should cause a warning. So here we can see the warning F7.1, that the vibration failure prediction. So the vibration is over the limit. So it means that something may be wrong with this axis, and honestly speaking, with this axis is something wrong, and there is the problem with the wheel that is not fixed correctly on the axis. So when I stop the axis and I will fix this, and I will fix this axis more correctly. Now I can hear that there is no such a big vibration. And if we start this axis again, we have even maybe bigger. So let's estimate. So it wasn't a good solution, but we can hear that the vibration level is higher. What we can hear here as at least, and this value is also visible here. Yeah, so it wasn't just the fixing of this wheel, but maybe the tuning value is too high. So to prevent the deterioration of the axis, we should lower the tuning of this axis to prevent some failure in the future. Yeah, so now I reduced the level of the tuning on this axis, so it still operates quite fastly, but the level of the vibration should goes lower and lower. So in the max it was 7 point something, and it goes to the lower values of the friction. Yeah, so using this very simple thing, we can judge if the level of the friction is proper or it's not the proper one. And very similar things we should be able to see on our HMI. So I will connect to my HMI using the VNC client. And here I can demonstrate you the screens. And there are the ready screens that we can easily add from GT Designer. And here we have the functions related to the maintenance generally, and 4 of them are related to the machine diagnosis. And here we have the vibration estimation function. So the same values that we have here in MR configurator, we can see online in this view. And so in MR configurator, we have to refresh this data from time to time to read the current values. In case of the HMI, we see, but I need to select the proper axis, axis number 2. We see these values online. Yeah? So we don't need to refresh this data. We see these values online. And that is the, let's say, vibration. So the next thing is the friction, and to show you how does the friction works, the friction estimation and friction judgment. I will start the axis number 3. It is the axis that controls the XYZ application, but wait a minute, because I have some troubles with this axis to start it. Okay. So now you should see that axis X and Y is moving, and both in MR configurator or on the HMI, we can see the levels of the vibration here, but we can switch to the friction estimation. And here we can see online the values of the friction that are estimated by this axis. It is axis number, this station axis number 3. It is the X axis in the system. So we can see that the estimated friction, the dynamic friction on this axis is about 14%, and the static friction is something about 4. It depends on the direction also. It's in different directions that there are slight differences. And as you can see, the levels are not yet, let's say, judged, because as I said, it requires quite a long operation of this axis. So after some time, after more than 4 days, because it is more or less 90 hours required for the estimation, these values should appear. But here we can try also to lower the axis Z to the table, and it should cause that the friction will increase. And so here you can see that the level of the friction from 14 goes to 15 almost, but the axis, I think, is overloaded, so it's not pressing so hardly. So let's so now I turn the axis on, and we can see that this estimated value of the dynamic friction is going a little bit up. So from 15 it went to 17. So it may, let's say, indicate that something changed in this application. So it can be something normal. If we are, let's say, drawing something or milling something, but in some conditions, some application can indicate that we have some mechanical problem on the axis. So depends of the application. We can use this factor as something that shows us that something wrong may happen with our axis. And the last thing that I would like to show here is the belt and estimation of the belt tension. So I need to start this bigger axis, but first of all I will stop the axis. So now we have the axis, the long axis on the belt moving. So it is axis number 1. So I will switch to the first axis. And here we can see what is, let's say, most important for us, the static friction that is estimated. And here the estimation is not yet correct, it's not yet finished, because the vibration, the friction, it is estimated just in one direction. I set here the parameters of this axis not correctly yet. So we estimate the friction just in one direction, and axis, I think, should expect the friction in both directions. Sorry, let me check. It's not defined, so most probably it needs some additional time to, let's say, to estimate the tension, to see these values in this window. But we can base on the, because generally it finally uses the static friction that now is 5 point something. So if I release the tension of this belt, in a time this value should go lower. So now I set lower tension of the belt, and you can see that this value of the friction goes a little bit down. So in a time, because this estimation needs some time to estimate correctly this value, it takes even a few minutes to find out the correct, to, let's say, adjust to the correct values. But from 7 something, almost 6, it went down below 5 and a half. Yeah? So it's more closer to the 5 than to the 6. So here we can see also that the tension of the belt has the impact on the friction. And if we, let's say, looking at this friction, the static friction, we can see some information that the tension of the belt is higher or it is lower than the previous. So that's the monitoring of the tension of the belt. In case of the gear, I don't have here any gear, so I cannot demonstrate it. So from my side, now it's, let's say, everything what I wanted to show you. So, gentlemen, now it's your turn back.
Okay, so we are back. hope that you can see us and hear us again. So, Adam, thank you for this very beautiful, let's say, presentation. Very good. So I think more or less everything goes according to the plan, and everything that we wanted to show was shown. So now, two things. We'll go back to the presentation because we have like 5 minutes maximally, something to tell more about the usage of this function in complete application, let's say. But once again, we are reminding you that if you want to, on the top, this is this bar, this blue bar. You can register. You can ask us a question. We will show you where we can, let's say, use this function in your factory. And if you want to, you can register. Yes. Okay. So once again, we'll go to the presentation. After that, we'll answer your questions.
Okay, so let's summarize it. First application, the application of dynamic resistance estimation can in fact be used in testing the assembly of consecutive machines when we have a repetitive production of these machines, inspection of the machine at the end customer side in the sense that we will know the changes resulting from our lack of maintenance, and reduction on unplanned downtime. The static resistance estimation application can be used to monitor belt tension, which is not easy to diagnose. Algorithm will show both over-tensioned and under-tensioned belts. These two types of algorithms can work in both Mitsubishi and third-party communication types, field buses, currently with CC-Link IETSN or with EtherCAT, for example.
Yes, CC-Link IETSN as our own network, yes.
And there are no differences in operation here. What's more, the entire operation of these algorithms is on the amplifier side, so there is no necessary to use any additional software. We only have to exchange the data with the amplifier and of course turn on the algorithm. And last but not least, the gear backlash measurement application. Unfortunately, this can work only with our software and only in service mode to the characteristic of the tests, and only allows gear backlash to be checked for low precision systems.
Yes.
That means for planetary gearboxes, it doesn't work correctly.
Yes, in our software or in our AGI, as Adam showed, yes.
Yes.
Yes, so let's say this is all from our side, from the side of the presentation, from the side of the test. But before you leave, please let us invite you to the next webinar. It will be about designing energy efficient application with servo drives. So we'll talk about very popular and very neat topic, energy efficiency, but with servo drives and how to build energy efficient application. It will be in approximately more than 1 month time. Yes, the same time, 10 a.m. And 6th of June. Yes. Okay.